I guess first of all, thank you guys for joining us tonight, and welcome to this talk on how to apply some of the things that Patrick just talked about in practice to a serverless application. So I guess Patrick already covered what does it mean when we talk about chaos engineering, and I guess for the fact that you guys are here, you probably heard about chaos engineering already, and you probably heard about them from the companies like Netflix or Amazon, how they will kill servers in production at random to simulate different kinds of infrastructure failures that results in the loss of, say, EC2 instances, and see how the system holds up and whether or not they can still stay up when those infrastructure problems happen. It's certainly one way you can apply principles of chaos engineering in practice, but I think chaos engineering itself is much broader. So if you look at the definition of chaos engineering on the principles of chaos.org, which is easily one of the best places to go and read about the chaos engineering if you want to get started and understand its core principles. So it defines the chaos engineering as a discipline of experimenting on a system in order to build up confidence in the system's capability to withstand turbulent conditions in production. And it's becoming more important nowadays, and as Patrick mentioned, we are building more complex systems that are also more capable, but there are a lot more moving parts, which means that we have more complex and hard to predict failure modes. And the more moving parts we have, the more likely we're going to see some form of failure in one of those moving parts. And so chances are we're going to see failures happening more frequently as well, which means more than ever it's important that we do our best to safeguard the experience of our users when these failures happen, and it's why resilience is such an important non-functional requirement nowadays, and that's for everybody. But what does it actually mean when we say you have to build systems that are resilient? If you look at the dictionary definition for resilience, it says the capacity to recover quickly from difficulties or toughness. In other words, it's not about preventing failures. And that's important because, as Werner once said, everything fails all the time. And you have no control over when failures happen. All you can do is prepare yourself for when they do happen, and they will. Eventually, everything is going to fail. This can get corrupted, chips can burn out, and people can trip over cables and disconnect networks or computers. And sometimes you lose network connectivity because sharks apparently like to bite those underwater network cables that connects the internet together. As British people like to call it, we call it Sod's Law, but I think everyone else know it as Murphy's Law, that anything that can go wrong will go wrong. And the goal of chaos engineering is to identify these weaknesses in our system where failures can happen before they actually happen to our system and cause system-wide aberrant behaviors. And how we do that is we do that by using controlled experiments to firstly learn about how our systems actually behave when these failure conditions happen. In the same way that we write tests for our business logic, we also need to test our system's robustness and resilience against turbulent conditions that it will eventually face in production, which could be done in a number of different ways. It could be done through organized events such as game days, whereby, for example, you may gather together as a team, and one of you may decide to, I'm going to turn off networking on one of our servers, and then you see how quickly your colleagues are able to firstly identify the problem, detect that there's an issue, and notice that the problem is that we lost the network connectivity on one of the servers, and see whether or not you have enough monitoring and diagnostic tools in place. Or alternatively, you can do this programmatically by injecting failures into your system and just see how it handles them. Of course, like Patrick mentioned, we don't want to do this in production right away. We want to do this in, say, a dev or staging environment where we can be more comfortable, so that in case we do find a problem, it's not going to actually cause a production outage, because that's not what we want to do here. We don't want to actually cause problems. So my name is Yan Cui. I'm an AWS Serverless hero, and I've been working with AWS for a very long time now. I've been running production workload on AWS for over 10 years. The last couple of years, I focused primarily with serverless technologies, including migrating a social network to run pretty much entirely on serverless. That was a couple of years ago, and you can read about that experience on a series of blog posts in the link here. Nowadays, I spend half my time working with MIGO as a developer advocate. And the MIGO is a troubleshooting platform for serverless applications, where you can see you have one single place to go to see all of your traces, all of your logs side by side with each other, and you can easily find information about your Lambda function invocations and then see what are the different things that are used within that transaction. And the other half of my time, I spend working as an independent consultant, where I work with companies all around the world to help them go faster for less by adopting serverless technologies properly. And I do that through trainings, through consulting, and sometimes I work with clients to actually deliver MVPs or projects on their behalf. In my spare time, I've done a lot of blog posts, also video courses. I've done a few things with Manning, and also self-published a few video courses. And recently, I've been running a podcast where I speak with other people who are using serverless in production. So going back to the point about the chaos engineering, I saw this tweet recently asking, well, I mean, what's the point of applying chaos engineering to serverless specifically? Because surely AWS is doing that already against the infrastructure that you're using to run Lambda function already, right? It's a good question, but then again, when you look at everything that is on your stack that runs your application, it's not just the infrastructure, it's not just the platforms and the hardware that's important that can fail. The great thing about chaos engineering is that it's not limited to just your application as well. I'm sure you can use it to test your infrastructure or the platform, but you can also use it to test the people and the processes that you have within your organization. And with the great thing about building my application on top of managed services like Lambda is that AWS is doing all kinds of things to make sure the Lambda service itself and the infrastructure beneath your functions and your code are highly resilient. So as a customer, I don't have to worry about a huge class of failures, such as the hardware failures or individual servers dying. All of those are managed by AWS, and they're continuously testing their infrastructure to make sure everything is as resilient as possible. But just as we have the shared responsibility model for the security of applications run in the cloud, whereby AWS is looking after some of that, but you still have to look after security of your own application. The same ideas apply here, that even just because Amazon is looking after the basic building blocks for your application, the underlying infrastructure, the hardware, the networking, and the OS as well, to make sure that they are secure and they're reliable, I am still responsible for my application code. I can still use chaos experiments to identify weaknesses in my code, as well as in my organization and the practices and processes that I have in place there. So in terms of tools available to me, you've probably heard about Netflix's Simian Army, where you have a whole bunch of different monkeys for killing servers, for injecting latency, for killing an entire availability zone or even a whole region. You also have commercial systems like Gremlin, where you can automate a lot of these experiments on your infrastructure and give you a really good developer experience to manage the experiments you run, to schedule them as well. And also seen other open source tools that allow you to run Chaos Monkey logic through Lambda function. But ultimately, what about our serverless architecture itself? I mean, we don't have access to the servers that are running our code anymore, so there's no server that we can queue, but there's still lots of different application level weaknesses and failure modes that we can test. For example, maybe I have misconfigured my timeouts, or they're not aligned so that user-facing functions can time out before some internal API is talking to is timed out. Or maybe I'm missing some error handling, which is incredibly basic mistake to make, but also very, very common in practice. And in cases where, say, a downstream system is having an outage, maybe I'm missing a trick here by not having some fallback strategy in place so that I can return some cached or default response so that I can still continue to operate even when some of my dependencies are failing. So Goona, who is going to talk next, and he's also one of the AWS Serverless heroes as well, he published a very helpful library that allows me to inject failures into a Lambda function so that I can run different experiments against my application. And there are always 4 steps to any chaos experiment. Step 1, you got to know what normal looks like for your system. If everything's on fire all the time, then you don't have a steady state, and you probably need to get your house sorted out in order first and establish what normal working condition looks like in terms of your say 99th percentile latency should be below 500 milliseconds, or maybe there should be a certain percentage should be lowered as less than a certain percentage of errors per error, for example, so per hour. And once you know what normal looks like, then you can start to really hypothesize, well, what's going to happen if something was to go wrong? For example, if a server dies, or what happens if DynamoDB starts acting up because there's some problems happening within DynamoDB. And then you can inject failures to your application to simulate those conditions that you want to test. But you want to keep them realistic. It's really easy to get carried away once you start doing some of these experiments. And finally, after you run the experiment, you go through the data to look for evidence to either prove or disprove your hypothesis. Here you're looking at your metrics, your logs, your X-ray traces, or any other form of telemetry that you have that you're collecting, and you try to look for evidence that supports your hypothesis about how your system would behave. So, for example, using the failure lambda library from Goona, I'm able to really easily inject latency into a Lambda function invocation. So as an experiment, I may ask, well, what if a service that we depend on is having some elevated latency? How is the application going to cope with that? And a very simple setup would be, we've got some user-facing API Lambda function behind API gateway. And when a user makes a request to this API endpoint, the Lambda function runs. And to do its job, it needs to talk to some other API endpoint that you have, which is also serverless, and it's got API gateway and Lambda behind it. So if you look at this very simple piece of code, it's simple enough. All it's doing is making a HTTP request to fetch some list of restaurants, and then it returns that data to the UI, I imagine. If you look at the code, we actually have some error handling here already, that if we couldn't load the restaurants from this HTTP endpoint, we're going to return some default response, maybe some hard-coded list of restaurants that we know are always going to be available. So our hypothesis is that, well, if something was to happen to this endpoint, then our caller API is our caller function is gonna timeout HTTP request, and then the try catch is gonna handle this timeout, and then it's gonna return some default response, and everything should continue to work. But when you run this experiment, you might find that, oh, actually, it didn't work like that at all. All we got was some internal server error. We didn't get this rendered HTML page. So it turns out that my function did timeout after 6 seconds. And when you look at the logs, you can see quite clearly that, sorry, not 6 seconds, 3 seconds in this case, that we were trying to make the request to this restaurant's endpoint, but we didn't get a response back within the 3 seconds. So our function actually timed out before it got response. So in this case, our user-facing API returned a 502 to the caller. But if you look at the logs, the internal API actually returned a 200. So from the internal API's perspective, everything was fine. So it turns out we had a mismatch or misalignment of our timeout values, where the caller function, the user-facing API function, had a shorter timeout than the internal API function that is calling. So this kind of timeout or misalignment can happen all over the place, because you may have many different user-facing functions all calling some internal API, and that internal API's Lambda function would have its own timeout based on what makes sense for itself. But whereas all of your other user-facing functions may not know what that timeout is, so it's very likely for you to have some mismatch, especially when different APIs and different microservices are run and managed by different teams. Beyond that, there's also potential mismatches there, whereby API Gateway itself has got a maximum integration timeout of 29 seconds, but your Lambda function can run for a whole 15 minutes. So it's very possible for you to have a Lambda function that can outlast the API Gateway invocation. Not to mention that there's also other things you got to think about as well when it comes to Lambda specifically, because it's the Lambda timeout only applies to the execution time for your function. If you have a function that has got really large dependencies that takes a long time to initialize, you may find that, well, on occasionally during a cold start, you may actually end up running for longer than your timeout should have allowed for, because you haven't factored into account how long that cold start for those functions are. So for example, if you have, say, a function that's written in Java and using lots of heavy dependencies, then it's quite possible for you to have a cold start of a few seconds. So even if your expectation is that this function's timeout is configured to be 3 seconds, the actual response time that the caller can expect can be much longer than that 3 seconds, because you have to factor into account how long cold start itself takes as well. So turns out there's quite a few different things that can possibly go wrong, even in a very simple scenarios that we have here, where there are lots of different ways where those HTTP communication can go wrong. Not to mention the fact that if we just rely on some of the defaults from HTTP client libraries that we use, many of those will have default timeout of 60 seconds. So in terms of how do you set the timeouts correctly, how do you handle these kind of timeout scenarios, I've seen two main strategies. One is that you can divide your caller function's timeout equally across the different HTTP requests it has to make. So in this case, say our function has a timeout of 6 seconds, and it's making 3 different HTTP requests. So each request is going to get 2 seconds, but then some requests may get timed out, even though if we had just let it run, it had been fine because we have enough time to execute all of them. The other strategy is whereby we take a more optimistic view of things, and every HTTP request gets the full 6 seconds. But then our function ends up timing out, even though none of the individual requests took too long, but together they took longer than the 6 seconds that we had. So our function timed out before we were able to finish everything everything we're doing, and so our caller gets a 502. So luckily for us, when it comes to Lambda, we can actually find out how much time is left in the current invocation using the context object. So I think a much better strategy here in terms of how do we handle HTTP requests we're making and handling dealing with timeouts is we can then set the HTTP timeout for every single request based on how much time is left in the current invocation. But we're going to reserve some time at the end so that we can do any kind of recovery steps like logging the timeout event itself, publish any custom metrics that, okay, we try to talk to this other service and we had a timeout. Or maybe we can fetch some cached response from previous requests, or maybe from some shared caching somewhere. That way, every request in this case is going to be given the best chance to succeed, and even when it fails, there's some time left for us to do some recovery. But if together, collectively, those requests did end up taking too long, and instead of just letting the function timeout and return a 502 to our caller, which is not a great user experience, we can then do something like fetching a previously cached response or return some default response instead. And to do that, you can see that we can add a few lines of code to our get restaurants function that we had earlier, whereby first we're going to use the context object. In this case, I moved into a global variable to check how much time is left in the current invocation, and then I'm going to reserve some time at the end. So I'm going to set a timeout for the HTTP request itself, using the value that I have derived based on the amount of time that's left minus my reserve time for recovery. And then if the HTTP request succeeds, we can then take the response and then we're going to cache it somewhere. So that in cases where it does fail because we hit a timeout, then what we can do is let's just check, do we have some previously cached response we can return? If so, great. Otherwise, do we have some default response that we have bundled into our application so that we can always return something? So this is useful, where returning something is better than returning nothing at all and just give user a 502. The outcome, the result of doing some more extra work, I guess a few more lines of code, is that we end up with a system that is more resilient, which is exactly what we're hoping for here. There's, in terms of other errors that we can inject into our system, we can also say let our function throw an exception and see what does the system, how does the system handle it. This could be quite useful for background processing functions, whereby we want to check the retry behavior happens correctly, that we have the right DLQs and all of that set up, so that if there are some persistent errors happening with one of our, say, kinesis or SNS functions, that we're not just going to lose some events. And for API functions, so we can also just force it to return some HTTP status code. Again, very useful for testing API to API actions to make sure that we're handling the different possible scenarios here. Maybe sometimes we're missing some handling for fault 3, whereby we need to refresh our authentication token or something like that. Whereby you are, or maybe we can fill up the disk, the temp directory, so that if there are functions that relies on using the temp space to store some temporary data, then what happens if it runs out of space? Or in cases that we want to test what happens if you want to, say, talk to some other services and there's some networking issues happening, we can use the blacklist option from the failure lambda library to simulate those as well. So this could be useful for testing, for example, what happens if there's something wrong with DynamoDB and that there's an elevated error rate from DynamoDB itself. So in this case, again, very simple setup. We've got API gateway, Lambda, turn to DynamoDB, and our function to fetch some restaurant from DynamoDB is, again, very simple. Just one API operation against DynamoDB. And the hypothesis is that, well, something happens, then that's fine. The AWS CK has got built-in retry with exponential backoff and all of that. So everything should be handled just fine without us having to do anything. You run it, turns out it didn't work. And what actually happened was that my function, again, timed out after 6 seconds. So it turns out the DynamoDB client, for JavaScript at least, has a default of a maximum of 10 retries, with an exponential backoff that starts at 50 milliseconds. And the delay between each retry is calculated using this formula, which Mark Brooker, who is a senior principal engineer at AWS, he professed at last reInvent that this is his favorite formula of all time. And so when you crunch the numbers, the max delay between retries alone can easily push you over, say, a 6-second timeout that you set for a Lambda function. And all you need for that is to get a couple of throttle exceptions in a row. So it's quite possible that the functions can get timed out because of this excessive amount of retries and exponential backoff. In fact, this happens quite often, probably more often than people realize. For example, quite a few people have talked about this already. I've also found this blog post from a seed last year, which talked about the exact same thing. And luckily, the sort of workaround here is just to override the default configuration and set something that's a bit more reasonable in terms of the max retry count for your function. And we can also add a fallback for reads as well, so that if we can't read the data from DynamoDB, then we can fall back to previously cached results or some static response. And for writes, we can also, instead of writing to DynamoDB straight away, and where DynamoDB is not accessible, we can also queue those writes up to, say, SQSQ, so that if something happens, at least we've got some background process that can retry those writes later. So hopefully, if the problem is temporary, then when the problem goes away, then our sort of retry process in the background, we just pick it up and then finish the write. So again, this is what I probably end up doing instead, whereby I will overwrite the default so that I still have some retries, I still have the exponential backoff, but we're not going to retry for 10 times because my function has got a really low timeout value of only 6 seconds. And also, after response comes back, we're also going to cache it as well, so that in the future, if something does happen, something does go wrong, then at least I can have some cache response that I can fall back to if that's applicable for your application. Or in this case, if that's not available, I can also return some default set of restaurants here as well. Again, the outcome is that we end up with a system that is more resilient to failures, which is exactly what we're looking for here. So those are just a few of the different type of errors that I can inject into my Lambda function using the failure Lambda library. But there's a lot more. So those are just some of the application failures that I can test to make sure that my application can handle different failures correctly, there's a lot more you can do, including testing how your application handles spikes in traffic, or maybe different size of payloads. If you've got, for example, you are writing those files to disk, or you are loading them into memory, and your function is configured with 128 meg of memory, but then someone uploads a really large file to S3, triggers a Lambda function, and then your function runs out of memory. So basically, anything that can possibly go wrong in your application, you should be thinking about that as a potential scenario and test them to see how your application actually handles them, and then react accordingly. Because again, everything fails all the time, and you don't have to, and you shouldn't stop at your application layer either. Try and apply chaos engineering practices to your processes as well, and make sure your procedures are both effective and that everyone is familiar with them, and everything is well drilled to make sure that when problems do happen, they are identified quickly and rectified quickly, and as much as possible, your application should be self-healing so that it will just deal with those problems without requiring downtime. And that brings me to the end of this talk. I want to thank you guys again for being with us this evening. And also starting, if you want to learn more about how to build production-grade serverless applications, I'm running an online course in a few months' time. So go to this link to check it out. And as I mentioned earlier, I'm also spending most of my time as an independent consultant. So if you want to see how serverless can help your organization, or how you go faster and see how we can work together, then go to my blog, theburningmonk.com, to see the different services that I offer. And again, thank you so much, and hope you guys stay safe wherever you are.